Hello everybody. So today we're going to be seeing that how an integral can secretly contain permutations. So often we have seen that in calculus some combinatorial patterns appear, such as you can see factorials in the Taylor series and you can even see combinations in the extended binomial theorem. But permutations are something which we don't encounter as much inside of calculus. So here is an example which demonstrates that how permutations can secretly appear inside of calculus as well, and what is the reason for it. So for this problem, we're going to be working on the general expression for the integral of x to the m times ln x to the n dx. So basically what we're going to do is we're going to try to obtain a general solution for whenever m is not equal to -1 and whenever n is a positive integer. So the solutions for this secretly contains permutations, and it's going to be our job to try and find this out. So if you want, you can go ahead and try and solve this on your own and get a general expression and then try to figure out how a permutation appears in this. But then I'm going to do it right now. So first, let's just try to simplify this. So this is going to be quick. Just use a simple u sub. So this is going to be our main bubble. And then we can just sub all of this back into this expression. And then, so we need our x to the m. And then e to the u is x. So then this just becomes e to the mu. This becomes e to the mu because this is to the power of m. But then since we have dx as well, and then dx is equal to e to the u du, this e to the m and then e to the u multiply. So then e to the mu and then u will get added. So then in the end we'll get e to the m plus 1 u, and this is u, and then we'll get u to the n du. So this is going to be our main integral that we need to solve. Now as you can see, this is in the form of a polynomial times an exponential. So we can try and get a solution using integration by parts. But since the powers are variables and they are not numbers, we don't really have an idea of how many times we'll have to do it. So we'll use the tabular integration method to figure out what is the pattern. So we'll differentiate u to the n and then we'll integrate this. And then here is what you need to observe. So first let's put an alternating pattern. So on will continue. And then here is what you need to observe. So as we differentiate this, you will get something like this. Oh. And as you continue, in the end you will just get n into n minus 1, and then this will keep on multiplying forever until you basically reach 2, right? Since we don't know what these numbers are, this continues forever until you hit the end, which is 2 and 1. So then this will just be 2 and then 1, and then u would be 0. Since u is 0, this effectively becomes into 1 as well. So it cancels out, and then we just have this. And then if you kind of look at this, this is just n factorial, right? So we can write this in a much more simplified way instead of writing in this expanded form. N factorial. And then we have completely gotten rid of our variable, which is u. So we need to differentiate this one more time and then we'll get 0. We don't know what the sign is here. And then the same thing goes here. We keep on integrating it until we reach the bottom. And this. And then if you look at it, we got n factorial over here, and then in tabular integration you multiply slantedly, right? So then whatever the nth iteration is, the next iteration will be the one which we need for this, right? And then if this came in the nth iteration, this one will be the n plus 1th iteration. So the final term for this would be something like this. n plus 1 to the n plus 1 power times e to the m plus 1 u. And then now we can cross multiply. Goes on, and then this n factorial will multiply with this. So now to sort of deduce, this into a summation, we can try to see what the pattern is here. So let's try and match this up with like the iteration. So for our first iteration, we have u to the n multiplied with this, u to the n multiplied with this. So then we just get this. For our second one, we have minus n times u to the n minus 1 multiplied with this term. It's a bit squashed, but yeah. We get this. n plus 1 squared. Third one also, let's do it so we can understand this better. We'll have positive n into n minus 1 times the term with m plus 1 the whole cube. So this will be n into n minus 1 u to the n minus 2 times e to the m plus 1. This e to the m plus 1 term will be constant for the entire thing. And then so basically, do you try to spot a pattern in the coefficients here? Here the coefficient is just 1. Here it's n. Here it's n times n minus 1. And then by trying to do this, we can try to deduce the nth term as well. So the nth term will basically just be this, n times this. And then the sign here, the sign here will depend on whether n, the power of ln x, if it's a positive or if it's an even or an odd number. So then what we can do is we can just put a minus 1 to the n plus 1. Since this is starting from 1, we need to do n plus 1 so that the first term always remains positive, times n factorial times constant term. And then this would be n plus 1 to the n plus 1. This will be our final term. And then what you can observe here is that if we want to sort of obtain a general expression for this, we need to sort of figure out what these coefficients are. Since there isn't really like a numerical pattern behind them, what do these even mean? So what we know basically is that, I'll be erasing this. Here is where you have to try and spot the permutations. So let's see 1. How can we obtain 1 from a permutation? So if we have n, p is 0, this is n factorial over n minus 0 factorial, which is n factorial. This cancels out, we get 1, which matches up with this. And then if you have np1, this is n factorial times n minus of 1 factorial, which is equal to n, which matches up with this, but since it's alternating, we have a minus 1, that's not a problem. And then we have np2, which is equal to n into n minus 1, which matches up with the coefficient of this. And then for the nth term, we can go ahead. We have npn, which is n factorial by n minus n, which is 0 factorial, which is 1. And then we just have n factorial, which is the coefficient of this. So to effectively compress this very complex looking integral into one form, we can just use permutations. And then deriving the summation is a bit tricky and lengthy, so I'll just write the final form here. So it should be something like this. The top will be n plus 1 because that's the final iteration. We can start it from 1 and then we'll add a sign and then we'll start it from I plus 1 because we want the first term to be positive. And then we'll do that with n into p into I minus 1, because we want np0 to be in the first term, and then we started from 1, so it'll be I minus 1 in the R section of the np. And then we can do this with u, and then if you spot here, in the second iteration we have n minus 1, third one we have n minus 2. So this is 3 and this is 2, this is 2 and this is 1. So then we need to reduce whatever we are subtracting with from whatever the term it is in the iteration. So this will be n plus 1 minus I, and then we'll keep our e to the m plus 1 u. Okay, yeah, this is also important. E to the m plus 1 u is neither dependent on n or nor it is dependent on I. So we can just casually take this out. And then one more thing, the first term itself has m plus 1, and then this last one does as well. So technically what we can do is we can take an m plus 1 out as well. And then we'll just get m plus 1, not to the I, but to I minus 1, since we took one out. This is what you should be getting. And then you can see how we use permutations. So now you can get the entire u sub back, and then you'll get something in terms of x, and then it'll look different. I'll just put it, because why not? So we had e to the m plus 1 u here, and then we know e to the u is x, so we can just write this as x to the m plus 1. And then over here, inside this entire complicated expression, we just need to sub it here. U to the n plus 1 minus I. So then this should be ln x to the n plus 1 minus I. So this entire expression comes into this for every m not equal to minus 1, and for every n which is a member of positive integers. And then this works for everything. So what is important here that is to note is that how we can obtain permutations from integration. So usually permutations are used as something, in combinatorics for counting. So suppose you have letters that you want to arrange in a pattern. That's why you use permutations. This is a unique example of how one technique in mathematics helps explain another technique in mathematics, whether they are in different areas of mathematics. So this is like a really cool observation that you can spot. You can go ahead and try out this integral on your own and try it out with different values of m and n. Keep this in mind. And then you can see how permutations appear. It's a really cool pattern. Do go check it out, and thanks for watching.